All right, everyone, it's 10 a.m. I'm gonna get us started, and I'm assuming some folks will join us in the next couple minutes anyway, but we have a great agenda today, and I don't want to miss out on any of the time that we have for our speakers. So welcome today. It's the final training of the series, what property managers and site design professionals need to know about post-construction operation and maintenance. And as a reminder, I know a lot of you are coming back to us from previous trainings, but this training is made possible thanks to an MS4 Municipal Assistance Grant from Mass DEP with partners from the Pioneer Valley Planning Commission, Center for Watershed Protection, and Neponset Watershed Association. So for this project, we're delivering these live trainings, and then we're going to create on-demand online trainings for the Massachusetts development community. Now, the ultimate goal for these trainings is to increase the understanding of how to prevent stormwater pollution and also to design projects that comply with Massachusetts and federal stormwater standards. The on-demand trainings that we're going to be developing will be available later this summer. And they'll be comprised of a lot of the content that we're presenting during these live trainings and incorporating feedback from you. So we'd be really grateful if you would take the brief feedback survey that's going to pop up in your browser at the end of this training. And that feedback will help to guide us in developing a more effective on-demand trainings for the community later on. So a snapshot of today's agenda. We're going to do a brief icebreaker, but I'm actually going to be throwing in some fun tidbits throughout the training today. You'll see in a moment. I hope you'll all participate. We're going to then hear about post-construction stormwater regulations in Massachusetts from Newt Tedder of US EPA. We're then going to hear from Sean Donlon of SGH about the importance of maintenance on stormwater practices. And then Roseen is going to be talking us through a couple of topics, the first being designing stormwater practices for easier maintenance, and then retrofitting existing properties, followed by a case study. There will be time at the end for Q&A of all the speakers, and there will be some periodic moments during the training for questions, but these segments are going to be recorded, so please make sure you're muted throughout the speaker portions. And during the time where we're asking for interaction or questions, feel free to take yourself off mute, raise your hand, and ask your question, or post them in the chat box for our speakers to answer when we get to the Q&A at the end of the training. So an icebreaker. First, I'd like to start with a couple poll questions. I want to get an idea of the folks that are participating today. So the first poll question I am launching right now. I'd like to get an idea of what type of organization you are affiliated with. And I'll give you about 20 seconds. It shouldn't take long to answer this question. Are folks seeing the poll pop up?
No, it popped up and disappeared, Lee.
Okay. So let me try launching it again. All right, what type of organization are you affiliated with? All right, we have a little over 50% are engineer or site development consultants. We've got a developer online. We've got a few folks from government agencies, be that federal, state, or local. And one other. Feel free to specify in the chat box if you'd like. All right, the next poll I'm going to launch is to get an idea of how many people are participating today. So if you're participating just you from your office, your home computer, share that, but also there might be smaller groups of participants, and we'd love to get an idea of a more accurate representation of how many people are participating today. All right, so it looks like most of you are participating alone, but we do have some fun, engaging aspects of this training. So I hope you feel like you're part of a group. And then we've got a couple participating with small groups of 2 to 5. All right. So just a quick share. All right, so on to the icebreaker. We're going to be doing a few riddles today. I have a few to start us off, and as I said, you're going to hear some riddles pop up throughout the training today. But the first riddle is, what has to be broken before you can use it? Smelling salts, that's a good guess. A glow stick. Oh, maybe there are a lot of options. Books by. Well, this riddle seems to be applicable to many. I haven't seen the answer that I have pop up yet. Any other guesses? There you go, Rich. You got the answer, at least that I had for this one. An egg. My spirit. Great. All right. So the next riddle is, I have branches, but no fruit, trunk, or leaves. What am I? Oh, a river. I like that. The government, the river. Not the answer that I have yet. The library. Any other guesses? Rich for the win again. Yep, I have bank, but it looks like you all have some other really good answers for that one. All right, the last riddle before we get started with the training today. David's parents have 3 sons, Snap, Crackle, and what's the name of the 3rd son? Oh, that was good, David. Yep. And maybe that's because it's your name as well, but that is the correct answer, David. Okay, so introducing our next speaker, our first speaker for today is Newt Tedder. Newt is a senior permit writer in the stormwater permit section at the US EPA Region 1. Newt has been at EPA for 12 years and currently serves as the lead permit writer for the Massachusetts Small Municipal Separate Storm Sewer, or MS4, general permit. Newt is going to be talking to us about post-construction stormwater regulations in Massachusetts, and that will be followed by a brief Q&A.
All right, thanks, Lee. And now we go ahead and try to share my screen. Okay. All right, so we're going to get started with just development standards. We're setting the stage for the other 2 speakers that are way smarter than me. So I'm just going to give you like a kind of a brief sort of overview of how we get to development standards and what, as developers, what you see and what you're dealing with when you get into that site design and in that maintenance phase, and sort of where those things come from. Just in general, we know that as we move from a more forested sort of natural environment to that more impervious cover environment, we have really long-lasting implications on our watersheds, not only from water quality standpoint, but also from a volume standpoint. And what the different layers of government are trying to do here eventually is trying to mimic that natural hydrology but still maintaining that, the economic engine that is larger cities, towns, development. And each layer of government sort of puts their own flavor on what you finally see and do for your eventual design. And so that first starts with the Fed. So that's me at EPA. And in Massachusetts, the EPA writes the stormwater discharge permits for cities and towns across the state, known as the municipal separate storm sewer or MS4 permits. For post-construction standards in particular, we regulate down to 1 acre of disturbance. And what the requirements of the permit do is actually force cities and towns to come up with their own bylaws and regulations to implement what the permit says for all disturbances that are greater than 1 acre or more. So for new development and redevelopment, that's where you see your retention standards or your TSS and TP pollutant reduction standards that you have to hit. Those are if you ever come across those in a local regulation or bylaw, this is where they're sort of coming from. They're coming from this federal mandate that comes down to the towns to regulate post-construction stormwater runoff to certain development standards. There's also a requirement in there that the town develop a program to ensure the long-term maintenance of any stormwater control that is designed to meet those requirements. So any private entity that designs a stormwater control, the town needs to make sure that they have a program in place so that those SCMs get maintained and so they actually function properly. So when you see sort of a town having a program for inspections, etc., that's sort of where it's coming from, right? They have to have a program for their federal mandated like permit regulation compliance. Moving on from the federal, the state also gets involved here. So the state also has their own, initiatives and guidance manuals, and just their. And in Massachusetts, we actually have regulation under the Wetlands Protection Act for certain areas of land that are close to wetland area. So the state gets involved too, and they have the same goal here. It's that mimicking natural hydrology over the course of time, sort of like limiting the impact of development that's having on our watersheds. The state usually does this through stormwater manuals and design guides. So those actually are then incorporated into those town regulations and town bylaws that will dictate what SCMs or control measures, or in particular maintenance requirements, are for the different stormwater controls that are put in to meet those pollution reductions that are mandated by the federal permit. So they sort of work together, but we're moving down this onion, getting a little more granular every time. So we get the big federal sort of overarching, we got the state that's going to get a little more granular on how maintenance and how design needs to happen. And then you get right down to what most people are really familiar with, is those town-wide ordinances and requirements and regulations that need to be hit during development. This is where all of the federal mandates and the state handbooks sort of come together, but each town municipality can put their own flavor on it, right? So they can, have requirements that apply to less than 1 acre of disturbance, all the way down to every single piece of disturbance in town needs to meet a stormwater post-construction requirement for pollution reduction and volume reduction. They also can have specific requirements for maintenance, in particular on different SCMs that you use to meet those town bylaws. They can usually will rely on state handbooks and manuals, but they can be very different as far as inspections go. They can be specific to the community and what the community's priorities are. So the town is really on the hook here most of the time for coming up with a comprehensive stormwater bylaw that encompasses all the federal requirements and the state requirements and all the state handbooks. So there's a lot that goes into that. And this is where you can go town by town and see slight differences and changes that you might be used to. And then finally, there's the site, right? You get down to the site, you're in the town, but the site also has its own constraints and its own, unique pieces that you as a designer need to take into account, specifically for maintenance considerations or design considerations. And that's what we'll be getting into more today. And I think I now turn it back over to Lee, or do I go, or do we hit right in? You tell me, but I am done. Thank you.
Thank you, Newt. So we have a couple minutes for any questions for Newt. feel free to come off mute and ask your question or post it in the chat box. All right, while we're waiting for you to process, I know we threw a lot of information out at you. I will hit you with another riddle. All right, we have one question. Do you believe the laws should get stricter as they get more local?
And as a belief, maybe. I like it really depends on the makeup and character and priorities of the community. So the federal, 1 acre threshold was designed a long time ago. It was, it was written back in 1999. I think we know a little bit more about the impacts of stormwater overall, but that is a very general requirement that needs to be looked at a local level. So let's say you have all your development in town is less than 1 acre always because of lot size constraints. Well, then if you're only regulated 1 acre, you are really missing all of the construction. So in that case, yes, we should be regulating down to a acreage size that actually makes sense for the community that's implementing. So it's really community by community based, but what we should really be aiming for is trying to have good post-construction standards for the majority of development in each community.
All right, thank you, Nikita. That was a great question. And Rob posed another question. Is there an approximate time for the issuance of the next MS4 permit?
Yeah, so the next MS4 permit is currently being written right now and should be out by the end of this year, calendar year.
Thank you. All right, the next riddle for all of you. What has many keys but can't open a single lock? All right, looks like you got that one pretty quick. Correct, it's a piano. All right, I see another question for you, Newt. You can either answer that in the chat box or we'll bring that back up at the Q&A at the end of the training. But thanks, Sarah. We'll make sure to get to your question. But now I'd like to introduce our next speaker, and that is Sean. Sean has been involved in land development and the design and construction of sites and stormwater management systems for over 20 years. He maintains a construction supervisor's license and professional engineering license in numerous states and Canadian provinces. Sean Donlon is going to speak on the importance of maintenance on stormwater practices, and that will also be followed by a brief Q&A.
All right, thanks, Lee. Give you a moment here to share out. Okay, we're gonna jump right in. We got a bit to cover here. By way of a quick outline, I just wanted to give a glimpse at what we're gonna do, a brief introduction into some of the O&M considerations for stormwater BMP. Take a look at a sample O&M plan, which I'm sure the audience, being comprised engineers in large part, is probably fairly familiar with. And then we're going to look a little bit more closely at a few.
Sean, you're muted again.
Sean, I think you
And your screen stopped sharing.
Was unmuted before. Did we get any of that first slide?
Not much. We got the first maybe 30 seconds.
Let me try again. I came in the office and everything for good for good reception, and it didn't work out. Okay, let's try again. So I was just briefly covering the outline. We're going to do a quick introduction. Seems like I'm clipping out here again. What's happening?
You sound good to me now, Sean.
Okay, I'll keep moving. Just let me know, please, if we're not holding up. So we're going to take a look at a few different BMPs and the associated risks for lack of maintenance. And I'm going to end on an example here about how a lack of maintenance turned into a problem for a homeowner. First here, as I was saying, I'm sure most are familiar. This is an excerpt on the screen from a sample O&M plan. You may encounter this, as Newt was alluding to, if you're in a project that's subject to the jurisdiction of the Conservation Commission. These will be explicitly required as part of your stormwater management design and controls. However, as time goes on, this is becoming more and more prevalent at the jurisdictional level, right? They're required as part of even simple engineering submittals to municipal departments, as even small as quarter-acre development on residential projects, right? In terms of responsibility here, ultimately, that's the owner. Often that's delegated or sometimes delegated to a property manager. However, ultimately, if they're in the event of some downstream release or some issue downstream from the system not functioning, or again, as Newt was alluding to at the site level, as we're going to see here, the protection of your on-site infrastructure, is really a function of how well you're maintaining your stormwater BMPs. In order to keep those up and running, that would be a cost the owner would ultimately bear if they don't stay on top of proper operation and maintenance. Here's a sample O&M log and inspection form. You can see some of the
Sean, your slides aren't advancing.
Hey, Sean, we could maybe we could try to advance our version of your slides if you continue having trouble.
It looks like Sean has dropped off. I have to give him a minute to get back on.
Maybe we should switch. Rob, are you okay with us switching up the order possibly? And
Yeah, would be
If-
happy to, if that makes it easier. Well, we can get Sean back on just in a later order. That no problem at all.
Right, so then why don't I introduce you, Rob, so everyone knows who you are, and then we'll do your first presentation.
Okay, sounds great.
No, I don't want to give away the.
just bear with me here. I'm moving to another location. Hopefully this is a little better.
Sean, we're gonna hear Rob's first presentation, and then we'll come back to you so you can figure out what you need to do, and if you'd like, we can progress your slides for you.
Okay, let me email you my deck right now.
Okay. So I'll introduce Rob. Rob Roseen is the principal of Waterstone Engineering PLC, a small niche engineering consulting company specializing in the design, planning, and permitting of stormwater management and nutrient controls. He has over 20 years of experience in the design, testing, and implementation of innovative stormwater management. So we will hear first about the designing of stormwater practices for easier maintenance, and then we'll come back to Rob later in the training to hear about retrofitting of existing properties and a case study.
Okay, so now I just gotta see if I can figure this out. Let's see, share. It's always a little tricky with multiple screens. Which one are we talking to? Okay, I think we want this one. All right, well, you happen to be looking at my title slide here by chance?
Right now, we're just seeing a blank screen. Oh, now we're seeing your title slide.
Okay.
Yeah.
Just curious too, wondering if the connectivity issue was on Sean's end or just over in general. Is there any pausing or any of that stuff going on with mine?
No, it's very
Okay.
clear.
Okay, great. All right. So yes, okay. What I'm going to talk about today is designing stormwater practices for easier maintenance. I think in the realm of stormwater management, in particular low impact development, we've really progressed substantially over the years with respect to the design and understanding performance. And really, it seems that the next big phase of understanding and sort of evolution in of practice here is in recognizing how to design these things for easy maintenance, for long-term performance, and keeping the owners in mind. So no better example than to talk about some of the challenges that have been had in New York City, and I don't show these photos as an example really to poke fun, but more from the standpoint that we have a lot to learn from New York, where they've been investing hundreds of millions of dollars in green infrastructure retrofits, and there's a learning curve to that we can all benefit from. So this is an article from the New York Times, which says, it's titled "To the City, a Pollution Fighter, to Some Residents an Eyesore," and I think and this is a concern from multiple levels. One of them is at a municipal level or community level, we're trying to build support for stormwater management. This requires funding, and community support for water quality improvement efforts are important. And in these types of photos or things that folks get to see about stormwater management are not doing much to engender support for stormwater management. So that's one item. But the other aspect of it is that this is what you see here is a big problem from an aesthetics issue only, really, meaning that these systems are going to function fine. This will continue to act as a biofilter. But what you've just by not attending to the maintenance components of this well enough, what they've done is really created an enormous maintenance headache here that is unrelated to its functionality. So, and this is another real basic example of this. This isn't low impact development. This is just a catch basin, but it shows the poor selection of a catch basin in a condition where clogging could be expected. So this is in the fall. Leaf litter is abundant in the fall. That goes like clockwork in New England, and a different type of catch basin, one that was open on the face of the curb in addition to the flat on the road, would have prevented this. And this was just simply a clogged catch basin. So this is an example of the need for consideration of maintenance in our drainage systems. So with that in mind, if you think about the evolution of low impact development, if we sort of consider for a moment conventional septic systems, these are systems that we know work well and are proven to work well, in the right conditions. And it's a fairly straightforward combination of approaches that are used here. We have a septic tank, which manages essentially all the solids, floatables, and debris in there, and then it's supposed to just pass the liquids into a leach field or a drain field. Now, if that septic tank is well maintained over years, that leach field should continue to function, for a very long time. But we can all imagine that if we removed the septic tank from this situation, that leach field would clog in a matter of months, right? And the question is should stormwater infiltration be any different, right? There are certain situations with certain land uses, high intensity trash and debris land uses, where you might expect, where we can expect a lot of materials that can impact both the aesthetics and the functionality of our stormwater filtration systems. So with this, our goal should be low maintenance asset management with pretreatment. If we think that most pretreatment approaches are hugely inadequate, And as an example, this photo on the top right here, this is a New York City bioswale shortly after the install. This is a high intensity trash and debris environment. And what's used here for maintenance is just a little stone riprap at the entrance, which is really a disaster in the making, because we can anticipate that it will look like what it does in the lower photo. This is not the same system, but this is a system after winter, and it's full of trash and debris, and certainly not an asset in terms of aesthetics, right? The top photo is great. People are going to love that. The bottom photo on the bottom, people are just going to be, soon they're going to be dumping shopping carts in that. But the problem with the photo on the bottom is that's mostly an issue of aesthetics. From a functionality perspective, that system still continues to work. So what we need to do, our goal, is to use existing staff and equipment for standard catch basin cleaning, and to match the appropriate land use and trash and debris with pre-treatment, and to separate maintenance for aesthetics and functionality, right? If you think about what we have, in general, we want to be on a 1 to 2 year cycle for BMP maintenance for functionality. In that photo on the bottom, we'd probably be on a 2 week to 1 month occurrence for aesthetics. That's a real, that's just an issue of poor design and consideration for pre-treatment. So if we think about the cost to maintain versus the cost of pre-treatment, a standard catch basin cleaning by a Vector truck and personnel every 2 years might be, $160 a clean. I realize these numbers are going to vary by jurisdiction and where you live and all of that, but it's relatively inexpensive, right? You have a Vector truck that comes out, maybe they're doing 6 to 10 catch basins a day. You're hiring out a Vector truck at $2,000, $3,000 a day. So you're getting these down to a fairly reasonable and quick occurrence. Whereas cleaning a biofilter monthly for aesthetics with 2 people at 2 hours could translate to a price tag of more like, $2,000 a year, as opposed to $160 every 2 years. So if you think about the cost or the return on investment for some of the pre-treatment systems that we have out there, in most instances, you're looking at a return on investment of 2 years or thereabouts. So when we think about different types of pre-treatment that are out there, there's many out there. So and I'm just, with a short amount of time here, I'm just going to provide a short list here of things. But so on the low intensity side, we might be using these sort of stone strip check dams, similar to what was in the New York City bioswale, or a 4-bay with riprap, right? And these things work fine. They're okay for things like sediment. They're not great for a lot of trash, because soon you're going to have trash accumulating, and it's going to again be a real big eyesore. And it's the eyesores, the aesthetic maintenance that we're trying to avoid here. So then in the range of low to medium intensity trash and debris load, we have all sorts of things that are out there. We have things like the Rain Guardian, a CPS screen, a storm sack, a pig, and these are all great systems. The nice thing about the CPS screen and the storm sack and the pig, these are all retrofit systems, so they can just go, generally speaking, they can go right into an existing catch basin, or into an existing, like at an inlet. A Rain Guardian is more of a new build piece. And why these things are sort of limited to low to medium intensity is because of the capacity of these systems for accumulation of trash and debris. A storm sack does not just, and a pig and a Rain Guardian just don't have that much capacity. So a Rain Guardian, what that's going to do, it's going to track or capture the trash and debris on top of the grate. So all this cigarette butts and coffee cups and things like that are going to be captured on the top. So it is going to become a little bit of an eyesore, but the good thing is that it's in a location where it's very easily maintainable, so that you're not into the bioretention system. And then for the medium to high intensity systems, you have things like the Pretex curb system. These are things that are essentially curb inlets that are these sort of baffled chamber systems that have high capacity, and just pop the lid and vacuum them out. And then in the same light, you have systems like the snout, which are hoods that go over an outlet and capture all of the trash and debris inside your barrel. So, and why I mention those is because what you want to avoid is something like this as well. So pre-treatment is really important for low impact development, but especially true for infiltration systems. So a very common form of pre-treatment that I think is a real problem personally is and that is going to become a problem in the future as we use this more and more, are things like the isolator row. Now, isolator rows are great, and I'm not discouraging their use. I think they're fantastic and we should use them. What I am saying is that we should have a pre-treatment system ahead of an isolator row, because if anybody's ever paid for or had to be involved in the cleaning of subsurface chambers, it's very time consuming and costs an awful lot. So we can put isolator rows in line with subsurface chambers, and we can build them large enough that they probably only have to be cleaned every 2 or 3 years. But to clean all that gunk out of these chambers is a really big deal, and can be on the order of thousands of dollars a day. And for big systems, it can take multiple days, because what it requires is you have to go down there with a hydrojet, and typically, there's a vac on one side and a jet on the other, and then you're pushing out that large quantity of material that's being captured in there. Now, again, I'm not saying that we shouldn't be using isolator rows. I think these things are great systems, but that we should have a pre-treatment system ahead of that. So lastly, with that, I think we would, couple just quick points to touch on. Maintenance challenges are real issues, and deferred maintenance is common, right? So if we think about back to Newt's presentation, municipalities are wrestling with how to find funds for these added expenses of stormwater management. And so construction is one thing. Maintenance is really on the very bottom of the list in a lot of cases. So for planning for realistic maintenance is necessary, and focusing maintenance to the degree possible using existing protocols, labor, and equipment. And what I mean by that is we're not necessarily doubling our public works staff or our public works equipment to enable the cleaning of all these catch basins or systems that we're building. And that things such as like grassed bioswales are, in my mind, just perfect, right? Because if there's anything we know how to maintain, it's grass, and it's very easy. And you can, we can run mowers down a grass bioswale far easier than we can go in and pick out all the crud out of a bioretention system that has trees and vegetation and large bushy vegetation in there. So with that, I think I am done. Here's an example of a little residential subdivision where they have a pre-tech system in there, and they've decorated it for Halloween or for the fall or something. And with that, I'll stop. I don't know how I did for time, but see if we have time for questions.
Thank you, Rob. Yeah, we have a time for a question, one question, then we'll, I think Sean is set up and he can do his presentation.
Okay.
I don't see any questions. If you do have any questions for Rob, feel free to post in the chat box, and we can come back to it later when we do a Q&A with all the speakers.
Hey, Lee, I'm just now noticing some text in there that were for that they can't see the screen. I'm assuming that was for Sean and not mine, right? Mine seemed to run okay, didn't it?
Yes.
Yeah, that was from the past. Yep. Yeah.
Okay, thanks.
Yep.
Sam.
Thanks.
Okay.
All right. So Sean, do you want to try to launch your presentation again?
Yeah, let me do this. I'm gonna keep my camera off just in case. I got a hard line. So hopefully we're up and running. Let me see if the slides will advance and you let me know.
Okay.
They're going pretty quick on your end.
It's right now I'm seeing your PowerPoint view. It's not set up for, you're not presenting your slides.
Why don't, would you mind just sharing out on your end? I don't know what's going on here. This is a hard line too, so we must be having some bandwidth issues in the office.
Yeah, no problem.
Audio is coming through, okay?
It is, yeah. All right, I'm going to.
I can, I think I can request control from you if you don't mind. That should allow me to flip.
Oh, perfect. Yeah.
Okay. All right, I'm going to quickly zoom through this outline. Thank you for the patience. I think we'd have this figured out after a couple of years of Zoom, but here we are. Again, we're going to do a quick intro into O&M.
Sorry, did I flip that forward?
Yeah, if you click it all on your side, that's what's going to happen. Sorry about that.
Okay.
We'll look at a sample O&M plan and then take a little bit deeper dive into a few BMPs. I think we covered this a bit last time, so I'm going to keep moving here. Here, I think I may have covered some of this, but just quickly again, this is an example of an O&M plan, which I'm sure many in the audience are familiar with, right? This would be a plan you'd encounter, it would be explicitly required if you're in a project that's subject to Conservation Commission jurisdiction and the stormwater standards. But it's also becoming more prevalent that these are required at the municipal level, right? Just for a simple submission to the engineering department associated with new development or redevelopment. They're in some cases pursuant to MS4 commitments, at least their objectives pursuant to those. They're requiring O&M plans be submitted at the end of construction to put in place, proper operation and maintenance in post-construction. And ultimately, this all, is the responsibility of the owner. Sometimes that's delegated to a property management company or whomever the subcontractor may be to do this work. And we're going to take a quick look at some of the recommended and implemented frequencies for each of these systems as we work our way through here. Here's one aspect of that plan. This is a simple O&M log and inspection form. You can see a few of the BMPs here: catch basins, deep sump catch basins, stormwater quality structures, sometimes called proprietary treatment units, storm drain piping, et cetera. So it's not comprehensive, but we're just going to get a glimpse at a few of these as we work our way through. And here's another aspect of this. This is a simple one-page inspection form, in this case for a deep sump catch basin. This is common aspect of many stormwater management systems as sort of your first line of defense. You can see the typical fields here: owner, property manager, et cetera, all the obvious stuff. But if you look closer at the annotations around the detail for the catch basin, you can see some of the things that would need to be observed and maintained as required as you make your way through the life of one of these systems, right? You have framing grate, is it corroded, dislodged, still seating properly, things like that. Often you find issues with labeled as brick and mortar here, but grade rings, right? If there's a situation where at the surface the water is getting to these catch basins, obviously do your grading and their function in the landscape. But if there's a leak through the grade rings, you can have a situation where some of that sediment, some of that soil material gets swept through the grade rings and into the catch basin, and it presents as pavement degradation at the surface or a little bit of a sinkhole. And that's going to, you're going to want to keep an eye on that as you move forward. You have oil hood here. We just looked at that in the last presentation, but the idea here is to keep the floatables from making their way downstream. That needs to be in place and intact to perform its function, right? And of course, the sediment, right? Much of what we're going to see as we work our way through here is an idea that the we're trying to capture the sediment upstream before it makes its way into our on-site BMP, sure, but also and ultimately eventually not making its way off-site into receiving water bodies, right? So the depth of sediment is key for the deep sump catch base. And building on that here, you can see as this is a, as I was getting at, a pre-treatment BMP for sediment and other pollutants, the idea is some of the pollutants end up binding to the sediment. So by removing the sediment, you can help with stormwater quality and other dimensions as well. You can see in the upper image here, an example, this is a catch basin that suffered from years of lack of maintenance, and it filled up, nearly to the top of the structure. You can't see the outlet pipe anymore. And although the bottom right-hand image, this isn't a picture from the same site, it's sort of a stock image, but on this particular site in question, the entire downstream storm drainage system was occluded with sand and sediment to the point that it was no longer functional, and due to some environmental concerns at the site, we really couldn't do much about it and it needed to be abandoned. So it's a very significant risk in terms of impairment of that sediment capture, right? And then downstream effects. The rule of thumb, generally speaking, this is often prescribed. It's half the depth of the sump in terms of sediment depth. And the idea with that is after about that depth, the sediment tends to be resuspended and it can make its way downstream. These catch basins, as you can see in the plan in the lower right-hand side, they're often paired as part of a treatment train with a water quality treatment unit. There are various manufacturers out there for these. And the idea with that first line of defense, often in paved areas, being the deep sump catch basin, downstream, and in series, often the stormwater quality units further treat the runoff. These are sometimes there are various designs. This one on the screen here is called a hydrodynamic separator, where the hydraulics in the sump allow that sediment to filter out as it makes its way through the system before going downstream. Often, these are started off with a semi-annual inspection recommendation from the manufacturer, but as we just heard regarding the site use, in commissioning one of these systems, the idea is really that the sediment loading is a function of the site use. If you have a site that doesn't generate a lot of sediment, doesn't generate high concentrations of sediment in the runoff, the accumulation tends to happen a little bit more slowly, and then vice versa. If you have a highly loaded site that generates high loads of sediment, they'll tend to fill up a little bit more quickly. So there's a little bit more, you need to pay a little bit closer attention when bringing the systems online before you really understand the frequency with which you need to inspect these and maintain them, right? And the idea being, as I hope is becoming clear, that through this treatment train, you catch that sediment as at the source as close as possible prior to making its way downstream into your other on-site BMPs and ultimately off-site. Next in line, right, as you see sometimes downstream of those two BMPs we just discussed, here's a subsurface recharge system. This is a retention practice. The idea, as is also prevalent in the industry for developers, landowners, even as part of redevelopments now, to take and retain some fraction of the runoff from their impervious areas on site and infiltrate that back into the ground, both to contribute to groundwater levels where they're being depleted due to impervious coverage, but also to somewhat offset the effects volumetrically downstream, and in some cases with the more frequent lower depth rainstorms, they can, if you're sizing a system, say from 1 inch or 2 inch, that really should be no contribution downstream during an event of that magnitude. So they can help with, downstream flooding and things like that. As you can see in the photo in the upper left here, this is a photo midway through construction of a chambered type system. You can see the risers on either end of the system. As I think we just heard a few moments ago, the typical maintenance for one of these systems is a combination of flushing at one end, trying to pull the flushed water out at the other end, and in some cases you can pull one of these jet systems through it, but it can be quite cumbersome, as you can imagine. And the risk really here is the degradation of the performance of the system, right? They function by the exfiltration of that retained water into the soils. So as that sediment builds up, the system performance can degrade, and you won't be able to hit your target of emptying the system in what is often prescribed at 72 hours prior to the next storm coming through, right? Similar type system here. This is a detention system. The primary purpose of these systems is to provide some storage to help reduce the peak rates of runoff off your site as part of your development. As is quite intuitive, any appreciable amount of sediment occupying that volume will impair the function of the system, right? So the idea, although is often prescribed again at annual inspections or something like that, this should be downstream of that treatment train we've taken a look at so far. But sediment can make its way into these systems, and you need to keep an eye on it to preserve that volumetric aspect of the design and keep that volume there and available in case a large storm comes through and the volume is actually required to attenuate the peak rate. Again, similar procedure here. Flushing, in this case, the design was to allow flushing at one end of each of these rows here, and removal at the downstream end to keep the system clean and running. Again, I'm not going to spend a ton of time on this. This is for more of a rural setting where there's area for surface ponds, but a sediment forebay. Again, pre-treatment BMP, similar idea to the upstream BMP, the deep sump catch basin, where the idea is to catch sediment, some of the other pollutants before they're discharged to the next BMP in series stormwater basin, and then ultimately downstream receiving water bodies. And recommended maintenance 3 to 4 times a year. Mowing as appropriate if there's a large forebay and some grass. And the idea often here is to, if you can look closely in the bottom right hand image, there's a clean out marker. Rule of thumb is generally about 50% again. As that sediment accumulates, it needs to be removed. Oftentimes this requires a mini excavator or some equipment to get down there, or in a small system it can be done by hand. And again, the idea here is that impairment of sediment capture with lack of maintenance, right? So keeping that volume available for the sediment when the water quality events come through is key to the performance of this system. And lastly here, before our example, outfalls. I think as designers and often, owners and just sort of people that, layperson's understanding of a drainage system, I think we conceptualize the outfall something like the upper left-hand side, right? Where, free discharge, no tailwater effect, not a lot of sediment buildup, and it's, generally operating as in theoretical sense, right? But often in the bottom right-hand side, as we'll see in our example too, these outfalls can become clogged up. This can happen for a variety of reasons. Sediment accumulation downstream. You can imagine a tailwater condition with some slow-moving water that allows sediment to settle out near the outlet, vegetation growth near the outlet, and of course sedimentation from that upstream drainage system. You can imagine the first example we looked at with that heavy sediment load making its way downstream. Some of that can be deposited at the outlet, and ultimately the risk here is that if it's not performing as intended, you have hydraulic capacity issues, and you can have backwater effects upstream in your drainage system, which is a good segue here to our last slide. This is a brief little example. This is in a residential setting. That photo we just looked at on the upper left-hand side. This is an outfall on the property. Well, the owner, to his surprise, came down one day and found a flooded basement, and after a little digging, there'd been some rainfall in the previous few days. He was able to locate at the building department, and by looking around at the topography on the site, that there was a footing drain and there was likely to be an outfall somewhere. After a little bit of hunting, the outfall was identified. There have been roots growing up in the pipe, and sediment obviously occluding the discharge. And you can see after just restoring even a minimal amount of flow here in this photo, that the system was then performing as intended. It was able to draw down the groundwater level, and the flooding in the basement almost immediately receded. So it was a fairly simple example, but a risk that manifested as a result of, really in this case, the owner didn't know the system was even there, so he wasn't tracking it. However, I'm sure that is going to be very much on the radar moving forward. And although this is just a simple example for a residential setting, the resulting problem, that sort of upstream flooding, in this case in the basement, is very similar to an issue you'd see on a larger site, given a hydraulic restriction at an outlet anywhere. And with that, I hope everybody was able to hear the whole presentation. I'll open it up to questions. Right.
All right, do we have any questions for Sean? All right, you can feel free to post those in the chat box if any come up. And while you're processing all the content that Sean presented, I have a couple more riddles, and then we will hear from Roseen again. All right. The next riddle is, what can you hold in your left hand but not in your right? And I actually cannot see the chat box right now. So, Deb, if you could call out some answers.
Right hand.
Close. Close to
Ah,
the answer to have.
left elbow. Left elbow.
With your left hand. It's your right elbow.
Oh,
Very close. All right. The last riddle I have for you today.
that was,
What time is it? Sorry, what was that, Deb?
I
The
nothing, I was
last
trying to figure out the riddle.
Oh.
Sorry.
What time is it when an elephant sits on a fence?
I'm seeing time for a new fence.
Yeah, that's very close to the answer. Time to fix the fence. All right,
Time for a new pet.
time for a new pet. I like that as well. All right, so we're going to get back to our regular training schedule and hear from Roseen about retrofitting existing properties.
Okay. All right, so this next one is a simple resource for BMP retrofitting and design for Massachusetts MS4 communities. So this is a project that was done with Patty Gambarini from the Pioneer Valley Planning Commission, one of the co-organizers of this training. And what we have here is, let's see, there we go. So, and you can find this at the Think Blue Connecticut River website. And what we've developed here is a set of green infrastructure BMP design standards and performance templates. It's kind of a mouthful. And show you what that is. Okay. So the green, well, actually, let me, before I, no, I'm not going to spell that. So to start with, the green infrastructure BMP design standards and performance templates. What this is it's a package. It's roughly a 20-page sheet set of green infrastructure design standards. And what I mean by that is these are actual plan sets of green infrastructure designs that are intended to supplement both the forthcoming updated MS4 handbook and to help communities with MS4 compliance. So the idea with this is that it provides municipalities and developers a set of readily implementable and standardized designs for 5 BMPs that are optimized for nutrient removal, size, and ease of maintenance. The BMP designs are generally in the categories of biofiltration, infiltration, and a dry pond retrofit. These are designs that can be essentially pulled from the shelf, and they're intended to enable municipalities to feasibly include stormwater retrofits in their capital improvement projects as a matter of routine. All right, so just because, as every good engineer does who's conscious of liability, I'm going to put note that this method does not replace the need for design by a qualified professional engineers and intended to be used as a tool to supplement. That isn't to say that it's eliminates the need for understanding of design knowledge here. Okay, so the design elements, what we have in this package is there's 5 standardized BMP designs for water quality and resiliency. The design templates are for different catchment areas, for ranging anywhere from a 1/10 of an acre up to 1/2 an acre. And if your sizing of for your drainage area is different than that, you can use multiples of this in terms of the dimensions. And what this provides then, and I'll show you all this, are tables of dimensions for the system's length, width, depth, storage, tables of performance, estimated costs of construction, and this sizing and performance information and costs are all from the UNH Stormwater Center BMP performance calculator for MS4 permit resources. So this is something that is that you can assume is would be accepted by as part of your MS4, because this is essentially just a simplification of an MS4 resource. So it also includes a couple of other aspects to it. It includes pre-treatment alternatives. It includes a bunch of designs for low intensity land uses, low to medium intensity land uses, and medium to high intensity land uses. It discusses online versus offline configurations. These, in many instances, it makes sense to connect to existing stormwater infrastructure and provide under drains, but it's not always necessary. As an example, the New York City bioswales that I showed you, most of those are actually offline, and what they do is they put those in a sidewalk, and they have a curb cut on the inlet side, and they have a curb cut on the outlet side. And then at the end, there is a bunch of information in there about bioretention soil mixes. There's 3 soil mixes that are provided. There's the DEP standard soil mix. There's more of a high performance soil mix that was developed when I was at the UNH Stormwater Center, that seems to be easier to grow vegetation and has very good removal. And then a third option, which is essentially the high performance mix with some admixtures for phosphorus removal. All these soil mixes are fairly simple, non-proprietary mixes, and are something that that could be produced safe by a public works yard and just stockpiled for usage. So the overview is that we have the low to medium density roadside land use. So these would be for areas that are sort of rural, where we have roads with a substantial right of way on the side, and areas that we can build that we have roadside that we can work within. And these particular designs are bioswale tree planters or infiltration trenches. And then the detention pond gravel wetland retrofit, which I'll talk about again in a second. And then we have the high density urban land use designs, which are really more intended to be on the roadside, sort of sidewalk or curb setting. And this is an urban bioswale tree planter or a what we refer to as the urban Arlington infiltration trench. Okay, and then a detention pond gravel wetland retrofit. So the idea with these retrofits is that we've been using detention ponds in our developments throughout the last 20 years, and these detention ponds exist all over the place, and they're ripe for retrofitting with sort of a high-end system. And so this what you see here on the side is a plan set from an existing pond, a large detention pond, with a gravel wetland design that's in there, and essentially using so you have an existing pond that's sized for somewhere of like a Q25, for example, and then you can put a gravel wetland in which sized for about an inch, a 1 inch water quality volume or less, and it really just takes up a fraction of this system, and it really boosts the overall water quality. So enormous potential for MS4 usage there. So this is an example of what one of the sheets might look like. This was an urban bioswale tree planter. So you have the plan view here. Well, and actually, so each of these sort of has a graphic that enables you to kind of easily understand what we're talking about. But this shows something in a sidewalk setting with a little fence, and then this sort of subsurface piece. So this is shown as in an online configuration. So something where you'd be tapping into existing stormwater infrastructure. And what you have here is flow runs down an existing curb line into a curb cut, runs through the system. When it hits capacity, it runs back out and down to the next catch basin down the curb line. And necessary notes for construction, and then all sorts of different details throughout the system at different sections. So we have our inlet sections, we have our mid sections, and our clean outs. And then the sizing element, the way that works is, so then you have these standardized templates, right? And what you see here is there's certain dimensions which are fixed, and there's certain dimensions which will change based on sizing. So in this case, we have a length that will vary. And what you have is we have these sizing tables, and there's 20 unique BMP sizing tables for each different BMP. And the way these work is there's 4 rows and 5 columns. So the 5 columns they range from 0.5 acres to 0.1 acres. And then they range in the rows from for a type A soil, a type B soil, type C soil, and a type D soil. And there's some typos in here. And so what you would do in terms of design is you'd figure out, what's my drainage area. So and then what's my soil type, and then you would enter that particular piece. And what it looks like is something like this. So the design process, you'd evaluate your potential location for stormwater management retrofit. When I say that, I mean, let's say this is a roadside. Actually, let's do this as an urban Arlington infiltration trench. So it's in a downtown setting. This is going to go in place under a road, right next to a curb, next to an existing catch basin. So you'd have to evaluate the potential for utilities in the roadway and other potential conflicts. Then you determine your drainage area. So in the case of catch basins, that's often somewhere between 5,000 and 10,000 square feet of drainage area. So fairly small drainage area. And then you would find you'd go into your sizing and performance table. So how that works is, okay, I have my half acre system. So let's say I'm looking for something that's a 21,000 square foot drainage area on a type A soil. And then I'm going to decide how much runoff do I want to treat for this? And this is, am I going to size it for a full 1 inch storm, or am I going to size it all the way down to a 1/10 of an inch storm? And then the corresponding water quality volumes. So let's say, for example, I decide I'm going to use a 2/10 of an inch depth of runoff treated, so water quality volume of 0.2 inches. And then I'm going to go down and I'm going to look at what all this stuff means. So this gives me an idea of what my filter surface area is going to be. It would be 181 square feet. The length of the system would be 36 feet by 5 feet wide by 2 feet deep. So you can see what we've done here. All these systems are fixed in terms of depth and width. And what we're doing is just varying the length of the system. So this is something that would fit in a typical roadway. And, you know, as I said, if you didn't find the dimensions you could actually go back to the UNH Center Performance, their BMP calculator tool, which is an Excel spreadsheet, do it yourself, or you could figure these out and do multiples of this. So maybe you want to do something that is, instead of 180 feet long, you want to, maybe you want to do, let's say you want to do 4/10 of an inch. And I'm just going to make it twice as wide as 2/10 of an inch. And then you work your way down and you can look at the system performance. So this is often what we're doing in terms of trying to assess what level of performance do we care about. So at 2/10 of an inch, I'm going to be managing approximately 74% of the volume. So that's in terms of recharge. I'm going to be managing about 73% I'm going to get a 73% removal efficiency for phosphorus, a 92% removal efficiency for nitrogen, and so on down the line, right? And then we talk about system costs. And the next case study that I talked about was going to go into this in a real world example. But for this system, it would be treating 1/2 acre and a type A soil for 2/10 of an inch of water quality volume. I could expect to be able to build this system for about $9,000. And then I have these unit costs. So these removal costs, these are essentially the unit performance. And these numbers probably will sound fairly Greek to most folks at first, but the more you begin to stare at these, the more you'll begin to understand kind of what they mean. But as an example, this is saying that we're removing per pound of nitrogen, this is the dollars per pound of nitrogen per year. So approximately, it's costing me about $1,400 per pound of nitrogen for removal. And you can see if we plot this on a curve, what you'd see is that it gets very steep, and we're past a point of no returns here. Actually, I'm sorry, not steep. It's plateauing here. So we're getting much less efficiency for a high cost. So you can see, all right, I have a 100% removal efficiency for nitrogen at a cost of $6,000 a pound, or I can come down here to 92% efficiency at a cost of $1,400 a pound. So way more efficient to be going for a system that's fairly small. And maybe you decided that wasn't enough efficiency for you, that you wanted slightly higher removal. And you can see, okay, so I'm going to bump it up to 3/10 of an inch water quality volume. It's now I've gone from 36-foot long system to a 54-foot long system. Okay. So that is it. That's the green infrastructure design standards that you can find at this website at the Think Blue for Connecticut River. And with that, I'll open it up for questions for myself and or Patty Gambarini at PVPC. So I'm going to find my chat box.
So Rob, I have a question. This is Deb. I have a question about do some communities feel like there's a balance between trying to be really efficient versus kind of building in a factor of safety in case maybe they lose a little bit of capacity or the soils weren't quite what they thought? Is there any discussion back and forth about that?
Yeah. So this already factors in a factor of safety of 2 for your infiltration rate, okay. And this also uses a static water quality volume. So it's not looking at, so you could make these systems quite a bit. So what I've just told you is, in my opinion, now I think this is just a kind of a designer's preference piece, meaning that everybody has their own opinion on this. I think these systems are fairly conservatively sized already. But to answer your question, I think a little bit more generally, yes, I think it's very important to build in excess capacity because what that does is it allows for greater resiliency with respect to maintenance and other things, right? So that it becomes less maintenance sensitive. But those are all very important things. So that what it really comes down to is two things, right? It's going to be there's the rate of infiltration, which is one factor of safety, and then there's the other one, which is sort of the sizing element, which is how much water is the system going to hold, and are you sizing that system statically or dynamically? And dynamically means you're looking at the rate that it's decreasing in relation to the rate that it's flowing. I'm sorry, that it's filling. So the rate of outflow versus the rate of inflow, versus a static design, which is if that water were to fall instantaneously from the sky, which it doesn't.
Okay, great, thanks.
Yeah.
That's a great question, Deb. I have another couple questions for you, Rob. This one is from Diane. What is the best practice for amount of precipitation used for designing stormwater infrastructure, given the delay in updating official precipitation rates?
Yeah, that's a good one. I use the Northeast Regional Climate Center. I really like their stuff, and I think they're kind of continuously updating it. I'm not sure with what frequency, but it's definitely not like our like Atlas 14 or something like that. Although I think Atlas 14 has just been updated too. I personally like the Northeast Regional Climate Center stuff. It's very good, and you can just put in your zip code of the area you're designing in, and download the extreme precipitation depths for it. And that's where I like to, and you can find both intensity as well as storm depths there. I think that Diane, did you mean, does that answer your question, Diane? I think I got it, but I'm not totally sure. Okay, great. And then I see winter performance for green PMPs. So this is actually a great one, Mia, and one that I'll say that I believe it or not, and I'm not trying to be disrespectful here at all, but I think we've already. This is a great question because I think we've dealt with this. I was the director of the UNH Stormwater Center for about 10 years, and that was one of the first things that we began to look at. So that started back in, when did we do that? I think it was back in 2002. When we started the Stormwater Center. And at that time, there was a huge resistance in the Northeast, primarily from the older engineers about the winter performance of LID, and particularly filtration and infiltration systems. And we did studies on that for years at the Stormwater Center. And the simple answer to this is that all BMPs are affected by winter, whether it's a conventional BMP or a low impact development. And what we actually found was that conventional BMPs, generally speaking, perform even worse than LID BMPs in the winter. So, you know, for sure they did in terms of water quality. And one of the reasons for that is that the more subsurface a system is, the more immune to, or the more resistant it is to cold climate impacts. But with all that said, you know, if a system freezes solid, so that's true with any system, right? Like whether it's a pond or a bioretention system, you have to have bypass outlets that are configured in such a way that they're going to drain properly in winter conditions. Like we had a system recently that we designed that we had, our overflow grate was a flat grate, and we had some flooding problems with that. There was a spring melt, the bioretention system filled, and then it froze on the top of it. So what we replaced that with a beehive grate, and I knew better than that. We should have had a beehive grate in there. But there's always those concerns. So generally speaking, LID winter performance is actually quite good. Everything suffers in the winter.
Thank you, Rob. That was great.
Yeah.
And you have a case study to share with us, correct?
I do. So let's switch into that. Let me find that. Hold on. How do I find, where are you guys here?
If you don't mind, while you're getting that presentation set up.
Yeah.
um,
Sure,
oh,
go right ahead.
You're really quick. Go right ahead, and then we'll leave a couple minutes at the end for questions as well.
Okay. So we're actually, believe it or not, we're sort of on time, right? This thing, are we at the right time, Leah?
Yep.
Or are we?
We have till
10
11:30.
minutes. Okay. All right. So this one, I'm going to dive into the optimization piece a little bit more in depth. Give you a real world example of this. So not everybody's familiar with the idea of optimization. It's a fairly kind of new term that we're beginning to hear more about from the MS4 world. And the idea is if you think of the different categories of stormwater management, there's new development, which is a lot of what we're fairly used to thinking about: a 1-inch water quality volume. You build you have a site, a blank slate, et cetera. But then there's redevelopment, which in a lot of cases is just treated kind of as new development. But then there's retrofitting. We've got all these existing unmanaged areas. And what are we going to do there? And the idea is that in a lot of cases, it's you do what you can, do the best that you can with the space allowable, with the funds you have, right? And that's almost the definition of optimization. Do the best you can with the area and cost, area and funds that you have to deal with. So this is an example of that. So this is Little Hale Creek in Durham. And what is BMP optimization? BMP optimization is the process of BMP selection and sizing based on lowest cost and highest performance. For example, the unit cost, which as an example would be dollars per pound of nitrogen, or it could be dollars per pound of phosphorus. And there's a little known provision in the Massachusetts Small MS4 Appendix H, which talks about the need for BMPs to be optimized. And you know, this isn't really worked over too heavily yet, but what the idea with this provision of the MS4 is that it's driving us in the direction of trying to do this in the most cost-effective manner. So optimization is especially valuable for retrofitting and redevelopment because optimized sizing of a BMP typically is small size BMPs that maximize available space. Optimization can occur at multiple scales. It can be done at the individual BMP, or there's actually tools like the Opti tool and other ways of doing this, where you can do optimization runs at a watershed scale. So you can actually, so when we're putting together nitrogen control plans, as an example, we can often do this across a watershed where we can automate the selection process based on land use and BMP type, et cetera, to figure out kind of what the lowest cost option is. And that's a whole nother presentation, but it's a really sophisticated and powerful process. So one of the ideas about optimization is demonstrated really, really well by the slide from Mark Voorhees. And what this shows is two things. You have the line in orange is average cumulative percent of nitrogen as it relates to runoff depth. So I'll repeat that in 1 second here. The blue line is it in terms of volume of runoff. So the way you read this slide is that this is the cumulative percentage as it relates to runoff depth. So what you can imagine, what this is showing you is that let's take the runoff amount, that 74% of all runoff, cumulative runoff, is 0.9 inches and less. 74%. So that means on an annual basis, you can expect that 75% of our runoff, 75% of our storms in terms of total volume will be 9/10 of an inch and less. And this is where that 1 inch water quality volume comes from. So depending on where you're at, a lot of times that 1 inch is referred to the 90th percentile, and it's not quite showing up like that here, but it doesn't really matter. It's just a generalized tool that we have. So the same thing is true for nitrogen, and what this takes into account for is first flush. So nitrogen is a pollutant that washes off fairly quickly. So it dissolves in water rapidly. So what you tend to see is that the majority of the nitrogen is carried in the smallest storms. So what you see here is 45% of all of the annual nitrogen load is captured in 2/10 of an inch of rain and less, right? So what that's telling us is that our small size systems can capture an enormous amount of the nitrogen load. This is telling us that 76% of it is 5/10 of an inch and less. And remember, even though we're up here around the 1 inch to capture 98%, even if I'm capturing the smaller storms, I'm still capturing the beginning of that nitrogen in a smaller storm. So it's really a very effective way. So keep that in mind for this next piece I want to show you here. So this is a very busy slide, and this is my attempt at trying to explain a complex process in a fairly straightforward way. So what I want to show you is BMP optimization for two conditions: a 1/4 inch water quality volume and a 1 inch water quality volume. So let's take this top example. I'm going to provide treatment for 1 acre of impervious cover for a 1 inch water quality volume, so one bioretention system. That will remove approximately 12.7 pounds of nitrogen per acre per year. That's that mass. Here's my mass of nitrogen at a cost of $40,000. These are just planning numbers here. So I have my drainage area on top. I have my system here in the middle. I have my pollutant load reduction and my cost. Okay. That's what you're getting off of this pollutant load curve. So this pollutant load curve, the dark line is for a type A soil. And you can see, all right, a 1 inch water quality volume here. I'm removing 12.7 pounds. There's only 0.6 pounds of nitrogen that's actually leaving the system, that's getting by the system. Okay, but you can see this asymptote that's occurring. So I'm getting less efficient the further down I go here. It's costing me more to do less. The steeper the curve, the better off I'm at. So at a 1/4 inch water quality volume, I can remove 10 pounds. So I'm not removing 12.7 pounds, but I'm removing 10 pounds, but at a much smaller cost. So here's my example. Now, instead of using 1 acre for 1 inch, I'm going to do 1 acre, but I'm going to do this now across 4 acres. Each 1 acre, I'm going to design it for one system at a 1/4 inch water quality volume. So 1 acre here, 1/4 inch, 1 acre here, 1/4 inch, and so on down the line. So I'm now managing 4 acres with 4 smaller systems. Each is going to remove 10 pounds. So my total now is 40 pounds at the same cost of roughly $40,000. Okay, so the idea is that optimization using 4 systems at a 1/4 inch water quality removes an additional 27 pounds of nitrogen per year, or that's a 315% increase. And what that's showing me is, in this instance, I'm doing it, the 1 inch system is doing it at a cost of 3,000 pounds of nitrogen per acre per year, or the 4 smaller systems are doing it at a cost of 1,000 pounds per nitrogen per acre per year. So way optimized. So now let me show you what we did in a real world example. So this is Little Hell Creek. They were going to do a road reconstruction because they're doing a culvert upgrade. It was a small culvert that they're replacing it with an actual stream crossing. We have 2 outfalls. And so we have this amazing retrofit opportunity. We have our first drainage area here has 2 acres of impervious cover. Our second drainage area here has about 0.4 acres of impervious cover. Total drainage areas combined, impervious and non, amount to about a little over 6 acres, and a total phosphorus load of about 4.5 pounds and a total nitrogen load of about 40 pounds. Okay, so what we did here is we designed a bioswale on one side. It's hard to see the bioswale. It hasn't been mowed in forever, but it's still doing its job. So here's a bioswale in one corner. This is the idealized version of it looks like. It's got a pre-treatment system on the front of it to remove trash and debris. And then this is an under-drained system. The under-drain comes out somewhere down in here. I can't remember where. And then discharges back. So edge of road here, pre-treatment system here, bioswale here, and then discharging over. And then we have a tree planter on the other side. And reason we used this type of system is because on a very steep slope, and there's concern about system slope failure, et cetera. My personal preference would not have been to have done this, but this was, municipal engineers feel very, they wanted to be very, they're erring on the side of caution, right? They want to have a system that they really do not worry about. And this is absolutely a system that you do not worry about. So again, what you have is a roadside pre-treatment for trash and debris, which minimizes the need for maintenance inside this system. And then it discharges to just a large concrete box that has a whole lot of material in it and 2 trees in it. And then under drained and out. So this does not have this is not getting infiltration. This is just filtration. And when you look at the BMP performance and cost for this system, we have the bioswale, because it's such a large area. We were treating, if I remember right, it was about 4.5 acres in total acreage and about 2 acres of impervious cover. So we sized that for a 1/4 inch water quality volume. And here's our numbers. We're getting about 40% load reduction for phosphorus, about 76% load reduction for nitrogen. And the bid cost for the system came in at about a little over $15,000. So this is coming in at a drainage area cost a little over $3,000 per acre of drainage area treated. If anybody knows anything about like retrofit costs, that is a phenomenal cost. You do not get that very often. That's a great cost. And the reason why is there's very little cost associated with road upgrade, right? We're basically building something on the edge of pavement. This is all in the right of way. And we're down to a $600 a pound for $600 to $100 per pound of nitrogen. That is a phenomenal retrofit cost. You just don't get any better than that. For the tree planters, a little bit more. That system costs a lot. Remember, you're spending a lot of money on a precast structure, but even still, it was still, I think, fairly affordable. So we're in the range of $3,700 per pound of nitrogen. It's higher than I would normally like to do, but again, precast costs a lot. But then when you consider it all combined for all of it, we're down at around 1,100. So when you consider we're getting about a little over 2 acres of, that's not acres, but we're getting a little over 2 acres of treatment for the whole area at a cost of around a little over $1,000 per pound of nitrogen. We did really, really well. So that's it. And I'm a little bit over for time, so maybe time for questions if folks have any, or we can just let you go.
Thanks everyone for your patience. I know it's a few minutes after our 11:30 end time. We wanted to capture that presentation for our on-demand series that's coming up. If you have any questions for our speakers, feel free to post them in the chat box or reach out. I know there's one question for Newt that we said we were going to come back to, and that's from Sarah. Can you speak a little more about the requirement that MS4 permittees must ensure O&M of private BMPs? I feel like that slips past a lot of permittees. Is that your sense? Any thoughts on how to improve?
I think in general, yes. So a lot of the requirements associated with asset management, in particular, being able to track and make sure that private assets are also managed properly, was a new thing for this MS4 permit. And I think in general, yes, a lot of those requirements did slip by, and it's a new thing for municipalities to think about. And it comes about because you are, as an MS4 permit holder, responsible for everything that comes into your system. So you need to be able to determine that what's coming into your system is actually, getting the pollution reduction that you think it's going to be getting. As we move forward, that asset management, tracking, accounting, maintenance is going to become more and more prevalent in municipal operations. I think, it's not going away as a permit requirement. And if anything, if you look at where the permits are headed, they're sort of headed in the direction of more and more asset management and proper maintenance of it, of all of your assets, both public and private, to discharge into the MS4 system. And the more, we can make that, more tools we provide, the more we make that, bubble up to the surface of people's consciousness, I think the better. But for now, yes, I think a lot of that has sort of slipped through, and it's just because it is a very new requirement for everyone.
Thank you. Did that help, Sarah?
Yes, thank you. Thanks, Newt.
No problem, Sarah.
All right, I do want to share, I have contact information for our speakers. So if you did want to follow up, you can get a screenshot of our speakers' email addresses. And you can also reach out to me as well. I posted my email address in the chat box. But I do want to thank everyone for joining us today. If you've been with us for the entire series, thank you for chiming in each day of this 4-part series. And I hope you check out the on-demand trainings when they are released later this summer, just to revisit some of the great points that our speakers have made or to share with your colleagues. We hope that ultimately this is going to help the Massachusetts development community design better practices, help to meet the new regulations in Massachusetts and stormwater standards. So thank you for joining us. Thank our speakers. We really appreciate you sharing your experience and your perspectives on these topics.